Right now, you're falling through a hole in space 2 billion light-years wide. Scientists confirmed this back in 2013, and most people still have no clue. We live inside something called the KBC void, a cosmic desert where matter runs 20% thinner than it should. This emptiness warps our measurements of reality itself, making the universe appear to expand faster here than anywhere else, and breaking our most basic equations about how the cosmos works. We will journey through the discovery that shattered cosmology, explore why 90% of space sits hollow, and reveal what it means to exist in the cosmic outskirts. The story begins in 2013, when 3 astronomers counting galaxies noticed something that should not exist. Ryan Keenan, Amy Barger and Lennox Cowie examined 35,000 galaxies, mapping their positions across billions of light years, and the numbers came back wrong. Everywhere they looked near Earth, fewer galaxies appeared than should be there. Not slightly fewer, but 20% fewer. The pattern stretched outward in every direction for 1 billion light years, forming a sphere of cosmic emptiness with us near the centre. This was not some small gap between galaxy clusters. Standard cosmology says voids on this scale should not exist. The researchers triple-checked their data, used multiple galaxy surveys, examined the sky from different angles, and the results stayed consistent. Our galaxy and everything around it sits inside an underdense bubble of space so massive it dwarfs everything else we have ever observed. The discovery earned a name that sounds almost casual, the KBC void, using the initials of its 3 discoverers, but there is nothing casual about what it represents. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together and leave empty spaces between them, and that is expected. But a region this enormous with such a significant deficit of matter pushes the boundaries of what random chance can explain. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this large and this empty, and when they do, it requires exceptionally rare initial conditions. The statistical probability comes in at less than 1 in 1,000. Some scientists calculated it would take a 10 sigma deviation from average density, meaning it is so unlikely you might not find one in the entire observable universe. Yet here we are, living inside one. The implications began cascading immediately. If we reside in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to measure how fast the universe expands, are we seeing the true cosmic expansion rate, or a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, something called the Hubble tension. For years, scientists have measured 2 different expansion rates depending on whether they look at the ancient universe or the nearby universe. The numbers disagree by 9%, which sounds small but represents a crisis. Both measurements are incredibly precise, both should give the same answer, and they do not. If Earth sits inside a massive underdense region, gravity from the denser matter surrounding the void would pull outward on galaxies within it, and that would add extra velocity to their motion away from us, making the local expansion appear faster than average. Suddenly the conflicting measurements made sense. We are not measuring the universe incorrectly, we are measuring it from inside a hole. This realization changed everything, but it also raised an uncomfortable question that cosmologists are still grappling with. If our location is this unusual, can we trust anything we think we know about the cosmos? Cosmic voids are not truly empty, which makes them even stranger than their name suggests. When astronomers call a region a void, they mean it contains far less matter than average, but matter still exists there. The void around us has a roughly 15% of the normal cosmic density. Picture it this way. If a typical region of space has 10 galaxies in a given volume, the same volume in our void might have only 1 or 2. The galaxies do not vanish completely, they become rare, scattered islands in an ocean of near-nothingness. Between these lonely galaxies stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. No new galaxy clusters can form, no rich superclusters emerge, and the void stays a void. This emptiness has consequences that ripple through physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant, and the dominant force becomes dark energy, the mysterious pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down the expansion in those areas. Inside voids, gravity loses that tug of war. Dark energy wins decisively, and as a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which allows even faster expansion. Scientists confirmed this through careful observation, measuring how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the centre faster than cosmic expansion alone would explain, and something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls downhill from the mountains toward the valley, but since we are talking about space rather than terrain, that pull makes galaxies fall outward, not inward. The effect is measurable and significant. Our own galaxy is moving away from the local void at 600,000 miles per hour, driven by this gravitational imbalance. The interior of a void becomes a strange place for physics. Light travels through it, experiencing less gravitational influence than light passing through normal space, and this affects observations in subtle ways. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity in voids causes less gravitational redshift, showing up as cold spots in temperature maps of the early universe. These cold spots line up perfectly with where we observe large voids today, and this alignment is not coincidence, it is physics. Understanding what makes voids empty helps explain why they matter so much to cosmology. They are not just boring blank spaces between interesting galaxy clusters, they are laboratories where dark energy dominates and where gravity takes a back seat. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works. The KBC void around us might be unsettling because it makes us question our cosmic typicality, but it also offers a rare opportunity. We are positioned in exactly the right place to study the universe's most extreme low-density environments. The structure that contains these voids is far stranger than anyone imagined. The universe is not a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese, where dense matter forms walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density. These nodes shine brilliantly with millions of galaxies packed relatively close together. Stretching between them run filaments, long chains of galaxy groups that can extend for hundreds of millions of light years. These filaments form walls, vast sheets where galaxies gather in higher than average concentrations. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. This structure was not always obvious. For decades, astronomers photographed the sky and counted galaxies, but the true three-dimensional arrangement remained hidden. Distance measurements were poor, and galaxies that appeared next to each other might actually be separated by billions of light years, with one much farther away than the other. Only when scientists began measuring galaxy redshifts systematically in the 1970s and 80s did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution snapped into focus, and the universe had structure on scales nobody expected. The first major void discovery came in 1978, when two independent teams identified large underdense regions. More surveys followed, each mapping deeper into space and revealing an increasingly intricate web. The Sloan Digital Sky Survey, which began in 2000, created spectacular three-dimensional maps spanning billions of light years. These maps show the cosmic web in stunning detail. Filaments twist and branch like blood vessels, voids appear as dark bubbles sometimes 500 million light-years across, and the largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. On the opposite end of the spectrum, supervoids like the Eridanus void stretch 1.8 billion light-years wide, with even fewer galaxies than the KBC void. Together, these features paint a picture of a universe organised on scales far larger than anyone predicted. Galaxies are not the fundamental building blocks. The web itself is the structure, with galaxies just marking where the matter happens to concentrate. Why does the universe organise this way? The answer reaches back to the beginning. Immediately after the Big Bang, matter was not perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density. Some regions slightly denser than average, and others slightly less dense. These differences were minuscule, maybe 1 part in 100,000, but gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still, and less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments, and meanwhile the underdense regions expanded into voids. The cosmic web is essentially gravity doing its work over cosmic time, turning barely noticeable initial ripples into the grandest architecture in existence. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10% but contain most of the mass. This imbalance defines the universe's character. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness punctuated by occasional concentrations of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble, and that makes all the difference for what we observe and how we interpret the universe. The Milky Way is not at the centre of the KBC void, but it is close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual centre. That might sound like a huge distance, and it is compared to anything humans experience, but the void extends outward for 1 billion light-years in every direction from its centre, making our offset relatively small. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. This position is not random, and it has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely, in one of the dense filaments, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension would not exist. Our larger cosmic neighbourhood adds another layer to this story. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbour Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any normal standard, yet even this supercluster resides within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. The void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population of matter scattered through the void, one of the rare concentrations in an otherwise barren expanse. The local group is also influenced by another nearby void called the local void, which is distinct from but connected to the larger KBC void. The local void extends about 200 million light-years and sits adjacent to our position. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond. This motion is separate from the overall cosmic expansion. It is a peculiar velocity, meaning it results from local gravitational effects rather than the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate because they add extra motion on top of the expansion signal. Astronomers must carefully account for these local effects, but inside a supervoid, those effects are amplified and harder to separate cleanly. The void's influence reaches even farther. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that exceed predictions from standard cosmology. Entire regions of space are moving faster than they should be, flowing in coherent patterns driven by the void's gravitational imbalance. The KBC void creates a large-scale velocity field that affects everything within it. Galaxies are not just sitting in an empty region, passively expanding with the universe. They are actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. This makes our local patch of the universe more dynamic and unusual than the calm, uniform cosmos that standard models assume. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes, and that light experiences less gravitational interaction than light travelling through denser regions. The reduced gravity creates subtle effects on the light's wavelength and energy. Additionally, the void itself influences the distribution of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range. Beyond the shell, the universe returns to more typical density. This creates an observational bias. We are not sampling a random location in the universe. We are sampling from inside one of its most extreme features. Living in the void means living with systematic uncertainty about how typical our measurements really are. Every measurement you have ever heard about the universe's expansion rate might be wrong, not because scientists made mistakes, but because we are measuring from inside a cosmic hole that distorts the signal. The problem reveals itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space expands. One method looks at the cosmic microwave background, ancient light, from when the universe was just 380,000 years old. This light encodes information about the early universe's density and expansion rate. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec, meaning for every megaparsec of distance, roughly 3.3 million light-years, space expands at 67 kilometers per second. The second method looks at nearby objects with known brightness, specifically type A supernovae and Cepheid variable stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing their actual brightness to their apparent brightness as seen from Earth, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise with very small error margins, and both should give the same answer if cosmology is correct. They do not. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there is less than a 1 in a million chance it is just random variation. The KBC void explains why these numbers disagree. When we measure the expansion rate using nearby supernova, we are measuring within the void. The void's low density means less gravity pulling back on the expansion, and matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region, and this inflates the local Hubble constant measurement. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. But here is where it gets uncomfortable. If the void explains our local measurements, then those measurements do not tell us about the universe as a whole, they tell us about our weird local environment. The cosmic microwave background method is unaffected by the void because it probes the early universe long before voids formed, and that measurement might be the accurate one for the universe's global properties. This means most headlines you have seen about the accelerating universe and dark energy might be describing a local phenomenon rather than a universal truth. We have spent decades building cosmological models based partly on local expansion measurements, and those measurements might be systematically biased by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special location. The principle states that the universe should look roughly the same from any vantage point once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. It suggests we are in an unusual location, which makes physicists uncomfortable. Science has progressively discentered humanity from special cosmic positions. Earth is not the centre of the solar system is not the centre of the galaxy is not the centre of anything, and now we are supposed to believe we just happen to live inside one of the largest voids ever observed. The statistical improbability bothers many researchers, yet the evidence keeps mounting. The void exists, our measurements are discrepant, and the void's effects match the observations. Whether we like the implications or not, the universe might actually be lying to us about its expansion rate. Or more precisely, our location is causing us to misinterpret what we measure. The crisis this creates in cosmology runs deeper than most people realize. The Hubble tension is not just an inconvenient disagreement between two measurements, it represents a fundamental challenge to our understanding of cosmic evolution. Cosmology rests on a framework called lambda cold dark matter, or the standard model of cosmology. This model has been spectacularly successful at explaining observations from multiple sources. It accounts for the cosmic microwave background temperature fluctuations, the abundance of light elements like hydrogen and helium, the formation of galaxies, and the large-scale structure of the universe. For decades, it has been the consensus model because it works so well in so many contexts. But the Hubble tension suggests something is missing or wrong in this framework. When a model's predictions disagree with observations at the 5 sigma level, scientists must take that seriously. The tension matters because the expansion rate determines everything else about cosmic history. If the universe expands faster, it reaches its current size in less time, making the universe younger. Current calculations based on the cosmic microwave background put the universe's age at 13.8 billion years. But if the higher local measurement is correct globally, the universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters that appear to be 13 billion years old based on stellar evolution models. These stars would be older than the universe itself, which is impossible. Either our age measurements for stars are wrong, our understanding of stellar physics is wrong, or the higher Hubble constant does not apply to the early universe. None of these options are comfortable. The tension also affects our understanding of dark energy, the mysterious force accelerating cosmic expansion. Dark energy makes up about 68% of the universe's total energy content according to standard models, but its properties depend sensitively on the expansion rate. If the expansion rate is higher than we thought, dark energy's behavior might be different than current models assume. Some researchers have proposed that dark energy evolves over time rather than being constant, which would be revolutionary. Others suggest we need to add new physics to the early universe, perhaps an extra burst of accelerated expansion shortly after the Big Bang. Every proposed solution introduces new complications and requires evidence beyond just fixing the Hubble tension. Dozens of alternative explanations have been put forward. Some scientists propose that the measurements themselves contain subtle systematic errors that have been overlooked. Perhaps dust between galaxies dims supernovae more than accounted for, making them appear farther away and inflating the expansion rate. Or maybe Cepheid variable stars behave differently in different environments, biasing their use as distance indicators. These explanations keep getting tested and ruled out as measurement techniques improve. The measurements are solid. Other researchers suggest modifications to general relativity, Einstein's theory of gravity. Maybe gravity works slightly differently on cosmological scales than we think, which would change predictions for expansion. This route leads into controversial territory, because general relativity has passed every other test thrown at it. The void hypothesis offers a cleaner solution that requires less modification to fundamental physics. It simply states that we are in an unusual location, and our local measurements reflect that rather than reflecting universal properties. This explanation bothers people philosophically, but requires fewer assumptions than inventing new particles or changing gravity. Recent work has strengthened the void hypothesis by showing it naturally predicts other observations. For example, the outflow velocity from the void should affect not just the expansion rate, but also the motion of galaxy clusters in our vicinity, and measurements of these bulk flows match the void predictions. The hypothesis is making testable predictions that are being confirmed. Nevertheless, debate continues. Not all cosmologists accept the void explanation. Some argue that even a void as large as the KBC cannot produce a big enough effect to fully explain the tension. Others point out that supervoids this large should be rare, and finding ourselves in one just when we develop the precision to measure the Hubble constant seems suspicious. Maybe we are interpreting the data incorrectly somehow. The controversy remains unresolved, which is why the Hubble tension continues to be called a crisis. It is not just a number that is off, it is a signal that our understanding of the cosmos might be incomplete. Before the KBC void revolutionized our understanding of cosmic structure, astronomers had been discovering voids for decades, each discovery building toward the realization that we might live inside one ourselves. The history of void detection reveals how our picture of the universe evolved from a simple model of evenly distributed galaxies to the complex cosmic web we now understand. The first hints of large-scale structure came in the early 20th century, when astronomers noticed that galaxies seemed to cluster together rather than being randomly scattered across the sky. Edwin Hubble's work in the 1920s and 30s established that galaxies existed beyond our Milky Way, and that they appeared to group together in clusters. But the true three-dimensional structure remained hidden because measuring distances to galaxies was extremely difficult. The breakthrough came with redshift surveys. In the 1970s, astronomers realized they could use redshifts as approximate distance indicators. Light from distant galaxies gets stretched by the expansion of the universe, shifting it toward redder wavelengths. The amount of redshift correlates with distance, so measuring redshifts for many galaxies allows mapping their three-dimensional positions. This technique opened a new era in observational cosmology. The first major void discovery happened in 1978. Two independent teams of astronomers were conducting redshift surveys when they noticed something peculiar. Robert Kirshner and his colleagues at the University of Michigan were mapping galaxies in the constellation Boötes. They expected to find galaxies distributed relatively uniformly across their survey area, but instead they found an enormous region with almost no galaxies at all. The Boötes void, as it became known, spans about 330 million light-years and contains only about 60 galaxies where thousands should exist. The discovery was shocking because nothing in the cosmological models of the time predicted such large empty regions. Galaxies were supposed to cluster, but the spaces between clusters should still contain scattered galaxies. The Boötes void was different. It was genuinely empty on scales that challenged theoretical understanding. Initially, some astronomers thought the void might be an observational artifact, perhaps an area obscured by dust or a region where the survey was incomplete, but follow-up observations confirmed the void was real. The few galaxies within it showed characteristics consistent with living in an underdense environment. They tended to be smaller, less luminous, and showed signs of evolving in isolation without the frequent interactions common in denser regions. The Boötes void discovery forced theorists to reconsider how structure forms. If voids this large could exist, what did that say about the initial conditions after the Big Bang? Computer simulations of structure formation began incorporating voids as natural consequences of gravitational evolution. Regions that started slightly less dense than average would lose matter to their surroundings over time, eventually becoming nearly empty. The simulations predicted that voids should be common, occupying most of the universe's volume even though they contain very little mass. As redshift surveys expanded in the 1980s and 90s, more voids were discovered. The Center for Astrophysics Redshift Survey mapped galaxies in the northern sky and revealed a structure that became known as the CFA Great Wall, a massive filament of galaxies stretching across hundreds of millions of light-years. But just as striking as the filament were the voids surrounding it. The survey showed that galaxies were not distributed uniformly but instead formed walls and filaments enclosing bubble-like voids. This bubble structure became known as the cosmic web, a term that captured the interconnected nature of filaments and the emptiness of voids. The topology resembled soap bubbles, with matter concentrated in thin walls and nodes while voids occupied most of the volume. This structure was unexpected and required explanation. Why should the universe organize itself this way rather than forming a more uniform distribution? The answer came from understanding how gravity amplifies small initial variations. After the Big Bang, matter was almost uniform, but not perfectly so. Quantum fluctuations during the inflationary period created tiny density variations, perhaps 1 part in 100,000. These tiny differences were enough to set gravity to work. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their neighbours, becoming emptier. Over hundreds of millions of years, this process created the cosmic web. Overdense regions collapsed into filaments and clusters. Underdense regions expanded into voids. The structure we observe today is the result of nearly 14 billion years of gravitational evolution, starting from quantum fluctuations smaller than an atom. This elegant picture tied together quantum mechanics, gravity, and cosmology into a coherent story of structure formation. The 2-degree field galaxy redshift survey, conducted in the late 1990s and early 2000s, mapped over 200,000 galaxies and revealed the cosmic web in unprecedented detail. The survey confirmed that voids are ubiquitous, occupying the majority of space. It also showed that voids come in a range of sizes, from relatively small voids tens of millions of light-years across to enormous supervoids hundreds of millions of light-years across. The Sloan Digital Sky Survey, which began in 2000, took void mapping to the next level. By observing millions of galaxies across a quarter of the sky, SDSS created the most detailed 3-dimensional map of cosmic structure ever made. The data revealed thousands of voids, allowing statistical analysis of their properties. Astronomers could now measure void-size distributions, shapes, and density profiles with high precision. These measurements showed that most voids are roughly spherical and have density profiles that decline smoothly toward the center. The typical void has about 20 to 30% of the cosmic average density at its center, rising gradually toward the normal density at its edges. Voids tend to be separated from each other by filaments and walls, creating a cellular structure reminiscent of biological tissue. But among all these voids, a few stood out as exceptionally large. The Sloan Great Wall, discovered in 2003, is a massive filament of galaxies stretching 1.37 billion light-years, one of the largest structures ever observed. Its discovery raised questions about whether there was a maximum size for cosmic structures, or whether even larger features might exist. If filaments could be that large, could voids be equally enormous? The Eridanus supervoid, discovered through its effect on the cosmic microwave background rather than through direct galaxy counts, showed that supervoids comparable to the largest filaments do exist. At 1.8 billion light-years across, it rivals the largest known structures. But its discovery raised as many questions as it answered. How common are supervoids this large? Are they consistent with standard structure formation models, or do they require special conditions? This was the context in which the KBC void was discovered in 2013. Unlike the Boötes void or Eridanus supervoid, which were discovered by finding unusual features in distant observations, the KBC void was found by carefully analysing our local cosmic neighbourhood. Keenan, Barger and Cowie were not looking for a distant anomaly, they were trying to understand the distribution of galaxies around us. The realization that we ourselves reside inside a supervoid was more shocking than finding such structures elsewhere in the universe. Previous void discoveries had been interesting for what they revealed about structure formation, but they did not directly affect cosmological measurements because the voids were far away and we were outside them observing from a normal density region. The KBC void was different. If we live inside it, every measurement we make is potentially biased by our unusual location. The void affects not just what we observe, but how we interpret those observations. The history of void discoveries thus culminated in a profound realization. The cosmic desert is not just out there somewhere to be studied objectively. We are inside it, and it shapes our view of everything beyond. This shifted void research from an interesting side topic in cosmology to a central issue affecting our most fundamental measurements of the universe's properties. The voids we observe today began as infinitesimal quantum ripples in the first moments after the Big Bang. During a period called inflation, the universe expanded exponentially for a tiny fraction of a second, perhaps 10 to the negative 35 seconds. During this expansion, quantum fluctuations were stretched from subatomic scales to cosmic scales. These fluctuations created slight variations in the density of matter and energy. In some regions, density was a tiny bit higher than average, and in others it was a tiny bit lower. The variations were incredibly small, about 1 part in 100,000, but they were enough to set the stage for everything that followed. After inflation ended, the universe continued expanding, but at a much slower rate. matter began to clump together under gravity, and the gravitational pulling only amplified the initial density differences. Regions that started slightly denser attracted more matter from their surroundings, making them denser still, and this created a positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters of galaxies. Meanwhile, regions that started slightly less dense lost matter to their denser neighbours. As matter drained away toward the collapsing overdense regions, the underdense regions became even emptier, and these underdense regions evolved into voids. The process is called gravitational instability, and it turned barely perceptible initial ripples into the dramatic large-scale structure we observe today. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was only 380,000 years old. At that time, the variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree. But those temperature differences correspond directly to density differences. Warmer spots had slightly higher density, cooler spots had slightly lower density. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped these temperature variations in exquisite detail across the entire sky. The maps show a mottled pattern of hot and cold spots at various angular scales, and this pattern encodes the seeds of structure formation. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe. The match between predictions and observations is one of the great successes of modern cosmology, confirming that our understanding of how gravity shapes structure over cosmic time is largely correct. However, the simulations rarely produce voids as large or as deep as the KBC void, and this is where tension arises. The initial quantum fluctuations were random, so every region had some chance of ending up as a void or a filament, but probability distributions matter. Small voids should be common, medium voids should be less common, and extremely large voids should be very rare. The KBC void appears to fall into the extremely rare category, which raises questions about whether our simulations are missing something. One possibility is that the initial quantum fluctuations were not completely random but had subtle patterns that enhanced the formation of large voids. This could happen if inflation did not smooth out structure as uniformly as standard models assume. Another possibility is that gravity works slightly differently on large scales than general relativity predicts, which would change how voids form and evolve. A third option is that the universe simply has more variance in structure than cosmologists expected, making large voids less surprising. Each of these explanations requires further evidence. Observations of more distant voids in other parts of the universe would help determine how rare the KBC void truly is. If similar voids turn up frequently, it suggests the standard model underestimates structure variance. If they remain exceedingly rare, it strengthens the case for modified physics or unusual initial conditions. The quantum origin of voids is both elegant and unsettling. It means that the cosmic desert we inhabit traces back to subatomic processes that occurred before atoms even existed. Randomness at the smallest scales propagated upward to create structure at the larger scales. The universe's organization is not designed or predetermined. It is the consequence of random quantum fluctuations amplified by gravity over billions of years. This realization is one of the profound insights of modern cosmology. But it also means that our location within this structure is the result of chance. There is no reason we had to end up in a void rather than in a filament. We are here because the initial conditions in our region happen to be slightly underdense. That accident of quantum chance 14 billion years ago determines what we observe when we look out at the cosmos today. Dark energy represents one of the deepest mysteries in physics, and cosmic voids offer the cleanest environment for studying it. Understanding dark energy requires understanding how it interacts with matter and gravity, and voids provide laboratories where dark energy dominates almost completely. The story of dark energy began with a surprising discovery in 1998 that would eventually earn a Nobel Prize. Two independent teams of astronomers were observing distant Type Ia supernovae to measure the universe's expansion rate and determine whether expansion was slowing down due to gravity. everyone expected to find that gravity was gradually decelerating the expansion, perhaps enough to eventually halt and reverse it, leading to a big crunch. Instead, they found the opposite. The universe's expansion is accelerating. Distant supernovae appeared slightly fainter than expected, indicating they were farther away than they should be if expansion were constant or decelerating. This discovery shocked the physics community. Acceleration requires something to push space apart, working against gravity's pull. That something was dubbed dark energy, though the name reveals our ignorance rather than our understanding. Dark energy behaves opposite to normal matter and even to dark matter. Where matter and dark matter attract gravitationally, slowing expansion, dark energy appears to cause repulsion, speeding up expansion. The simplest explanation for dark energy is Einstein's cosmological constant, a term he added to his equations of general relativity to allow for a static universe. Einstein later called it his greatest blunder after Hubble discovered cosmic expansion, but the cosmological constant makes a comeback as dark energy. If space itself has an intrinsic energy density, that energy would remain constant as space expands. As the universe grows, the total amount of dark energy increases because there is more space, and this drives accelerating expansion. The cosmological constant fits observations well, but it raises profound questions. Why does dark energy have the particular value we observe? The value is incredibly small by particle physics standards, yet perfectly tuned to become dominant in the recent cosmic past. If dark energy were much stronger, it would have prevented structure formation entirely. If it were much weaker, it would be undetectable. The fine-tuning problem bothers many physicists, leading to alternative proposals. Some researchers propose that dark energy is not constant but varies in space and time. This dynamic dark energy, sometimes called quintessence after the medieval concept of a fifth element, would be a field permeating space similar to the Higgs field. The field's strength could change over cosmic history, perhaps being weaker in the past and stronger now. Testing whether dark energy is constant or dynamic requires measuring how cosmic expansion has changed over time. Voids offer exceptional opportunities for such measurements, because they are the only regions where dark energy completely dominates. In dense regions, gravity from matter is strong enough that dark energy's effects are overwhelmed or at least significantly modified. Galaxy clusters hold themselves together gravitationally despite dark energy trying to pull them apart. Even in filaments, gravity remains relevant, affecting how structure evolves. But in voids, the low matter density means gravity is negligible. Dark energy wins decisively, controlling how voids expand and evolve. This makes voids sensitive probes of dark energy's properties. If dark energy is constant, voids should expand at a rate that depends only on the energy density and the expansion history of the universe. If dark energy varies, voids might expand faster or slower than predicted, revealing the variation. Measuring void expansion is challenging but possible. One method involves studying how void boundaries move over time. The edge of a void is defined by where galaxy density transitions from underdense to normal. As the void expands, this boundary moves outward, and galaxies near the boundary experience peculiar velocities from the expansion. By measuring galaxy velocities at void edges and comparing them to predictions, astronomers can test whether voids expand as expected for constant dark energy. Early results suggest dark energy has been roughly constant over the past several billion years, consistent with the simplest cosmological constant model. But the measurements are not yet precise enough to rule out small variations. Future surveys with better data will either confirm dark energy as constant or reveal evolution in its strength, which would revolutionize our understanding of fundamental physics. Another way voids probe dark energy is through their shapes. If dark energy is truly uniform and isotropic, meaning the same in all directions, voids should maintain spherical shapes as they expand. Deviations from sphericity could indicate that dark energy has directional properties, or that other forces are at play. Current observations show most large voids are approximately spherical, supporting the idea that dark energy is uniform. However, some voids show elongation along particular axes. This could result from the surrounding structure, with filaments and clusters creating gravitational gradients that distort void shapes, or it could hint at more exotic physics. Distinguishing these possibilities requires detailed modelling of how gravitational tides from surrounding structures affect void evolution, compared to how variations in dark energy would manifest. The acceleration of void expansion has practical consequences for observations. As voids expand faster than the cosmic average, the density contrast between voids and filaments increases over time. Voids become emptier, and filaments become relatively denser. This means the cosmic web becomes more pronounced as the universe ages, with sharper contrasts between empty regions and dense regions. This evolution can be traced by observing voids at different distances, which corresponds to different times in cosmic history. Distant voids appear as they were billions of years ago, while nearby voids show their current state. Comparing void properties across cosmic time reveals how structure has evolved under dark energy's influence. These studies show that void expansion has indeed accelerated over time, consistent with dark energy becoming increasingly dominant as matter density dilutes. The KBC void, being local and large, offers unique advantages for studying dark energy. Its proximity allows detailed measurements of galaxy velocities and density profiles throughout the void, not just at the edges. Astronomers can map how expansion varies with radius, testing whether the void's interior expands uniformly as dark energy models predict. The void's large size means its expansion has been ongoing for billions of years, providing a long baseline for detecting any evolution in dark energy strength. If dark energy's properties have changed over time, the KBC void structure should show signatures of that change. The density profile and velocity field would deviate from predictions based on constant dark energy. So far, observations are consistent with constant dark energy, but uncertainties remain large enough that subtle variations could be hidden in the data. Improving these measurements is a priority for next-generation surveys. The relationship between dark energy and voids also connects to the ultimate fate of the universe. If dark energy remains constant and dominant, cosmic acceleration will continue indefinitely. Voids will grow larger, consuming more and more of space. Eventually, even galaxies within superclusters will lose gravitational contact as space between them expands too rapidly for light to traverse. The universe will become increasingly empty and isolated, with voids occupying an ever larger fraction of total volume. Some theories propose dark energy could strengthen over time, leading to a big rip scenario where acceleration becomes so extreme that even atoms are torn apart. Others suggest dark energy might weaken or reverse, potentially allowing gravity to reassert itself. Testing these scenarios requires understanding how dark energy behaves now, and voids provide the best laboratories for such tests. The void around us thus serves dual purposes. It challenges our understanding of structure formation and cosmological measurements, while simultaneously offering opportunities to probe fundamental physics. The same feature that makes the KBC void problematic for interpreting local observations makes it valuable for studying dark energy in its purest form. Understanding one requires understanding the other, and both are essential for grasping the universe's true nature and fate. When you picture the universe, you probably imagine a sky full of stars and galaxies, but the reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids. This is not just empty space in the sense of vacuum between stars, it is empty in the sense that entire regions hundreds of millions of light years across contain almost no galaxies at all. If you could travel through a void, you would fly for tens of millions of years at the speed of a light without encountering a single galaxy. The isolation would be nearly absolute. This distribution creates a lopsided universe. Most of the matter concentrates in a small fraction of the volume. The filaments are crowded with galaxies that interact, merge, and evolve rapidly. Star formation is vigorous, black holes grow, and galaxies collide and trigger bursts of star creation. Meanwhile, the voids are quiet. A few lonely dwarf galaxies drift through the darkness, separated by vast distances. These void galaxies evolve slowly because they rarely interact with neighbours. They tend to be smaller, fainter, and less evolved than galaxies in dense regions. Star formation is sluggish, and many void galaxies contain large amounts of neutral hydrogen gas that has not yet condensed into stars. They are galactic backwaters, isolated from the busy highways of the cosmic web. The extreme emptiness of voids raises questions about how empty space can really be. Even in voids, dark matter is present. Dark matter makes up about 85% of all matter in the universe, but does not interact with light, making it invisible to telescopes. It is detectable only through its gravitational effect. In voids, dark matter is much less concentrated than in filaments, but it still exists at about 15% of the cosmic average density. That might sound like a lot, but spread over such huge volumes, the amount of dark matter per cubic light year is incredibly tiny. Additionally, voids contain dark energy, the mysterious component driving cosmic acceleration. Dark energy appears to be uniform throughout space, so voids have just as much dark energy per volume as dense regions. In fact, because dark energy does not clump like matter, it becomes the dominant component in voids where matter is scarce. The interplay between dark matter and dark energy determines void evolution. In the early universe, matter dominated even in underdense regions, and gravity still mattered. As the universe expanded and dark energy became more important, voids began accelerating their expansion. This acceleration makes voids grow faster over time, eating into the surrounding filaments. Eventually, if dark energy continues to dominate, voids will consume more and more of the universe. Filaments will thin out, galaxy clusters will become isolated islands in an expanding ocean of emptiness, and billions of years in the future, the universe will be even emptier than it is now, with voids occupying an even larger fraction of the total volume. This future evolution is inevitable, given what we understand about dark energy. The universe's destiny is to become increasingly hollow. Understanding the void fraction of the universe is important for interpreting observations. When we measure the average properties of the universe, such as the overall matter density or the expansion rate, we are averaging over both voids and filaments. If we do not account for the fact that most space is void, we might misinterpret what those averages mean. For instance, measurements of the cosmic microwave background give the average matter density of the universe, which is about 30% of the critical density needed to stop cosmic expansion. But that average includes both the dense filaments and the sparse voids. The local density varies dramatically depending on where you are. In a filament, the density might be 3 times the average, and in a void, it might be 15% of the average. These variations matter when trying to understand local observations. The 90% void fraction also affects searches for rare phenomena. For example, astronomers searching for distant supernovae or gamma-ray bursts are most likely to find them in the dense filaments, where star formation is active. Finding these events in voids is much rarer because voids contain fewer galaxies and less star formation. This creates an observational selection effect. Most of the interesting astronomical events happen in the busy 10% of the universe, not the quiet 90%. We study the universe from within the active regions and mostly ignore the empty ones, but the voids are just as much a part of cosmic reality as the filaments. Understanding them is essential for understanding the universe as a whole. Baryon-acoustic oscillations are frozen sound waves from the early universe, and they have become the most reliable ruler for measuring cosmic distances. In the first 380,000 years after the Big Bang, the universe was a hot plasma where matter and radiation were coupled together. Sound waves rippled through this plasma, creating oscillations in density. When the universe cooled enough for atoms to form, the sound waves froze in place, and the distance these waves travelled before freezing left an imprint on how matter is distributed today. That distance is about 490 million light-years, and it shows up as a characteristic scale in the clustering of galaxies. Astronomers can measure this scale and use it as a standard ruler because the physics that created it is well understood. This ruler works at any distance. Whether you look at galaxies nearby or billions of light-years away, the same characteristic scale appears in their distribution. By comparing the apparent size of this scale at different distances, scientists can map how the universe has expanded over time. It is like placing identical meter sticks at various distances and measuring how big they appear. If the universe's expansion is accelerating, distant meter sticks look smaller than they should. If expansion is slowing, they look larger. The technique is called baryon-acoustic oscillation analysis, and it has revolutionized distance measurements in cosmology. Unlike other methods that rely on the brightness of objects, which can be affected by dust or other complications, the baryon-acoustic oscillation scale is purely geometric. Using this technique, researchers have mapped the 3-dimensional distribution of galaxies across billions of light years. These maps reveal the cosmic web in unprecedented detail, and they also reveal the KBC void. When scientists analyse galaxy distributions in our local region and compare them to predictions from baryon acoustic oscillations, they find a clear deficit. The void shows up as a region where the observed scale of galaxy clustering differs from what distant measurements predict. This mismatch is exactly what you expect if you're inside an underdense region, and the baryon acoustic oscillations provide independent confirmation that the void exists and quantify its depth and extent. The measurements are not simple. Mapping galaxy distributions requires massive surveys that observe hundreds of thousands of galaxies and measure each one's position and redshift. Projects like the Sloan Digital Sky Survey and the Baryon Oscillation Spectroscopic Survey have spent years collecting this data. Processing it requires sophisticated statistical analysis to extract the baryon acoustic oscillation signal from the noise of random galaxy positions. The signal is subtle, typically only a few % stronger clustering at the characteristic scale compared to other scales, but modern surveys are sensitive enough to detect it reliably. They have measured the baryon acoustic oscillation scale at multiple cosmic epochs, tracing the universe's expansion history from when it was about half its current age to the present day. These measurements have revealed something surprising. The expansion history appears to deviate slightly from predictions based on the cosmic microwave background. The deviations are most pronounced at low redshift, meaning recent cosmic history, and they align with being inside the KBC void. Galaxies within the void show redshifts that are slightly higher than expected for their distance when using the baryon acoustic oscillation ruler. This is consistent with the outflow velocity adding to the cosmic expansion signal. The baryon acoustic oscillation measurements thus provide another piece of evidence for the void and its impact on our observations. They show that the Hubble tension is not confined to supernova measurements but appears across multiple independent techniques. The precision of baryon acoustic oscillation measurements continues improving with new surveys. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is mapping tens of millions of galaxies with unprecedented accuracy. These measurements will allow much finer mapping of the void structure and velocity field. Within a few years, astronomers will know the void's properties to within a few % uncertainty. That precision will either confirm the void as the explanation for the Hubble tension, or reveal additional complications that require further theoretical development. Either way, baryon acoustic oscillations are proving to be an essential tool for understanding our cosmic environment. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to shatter it. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special or different from any other when you average over large regions. Isotropic means the same in all directions. The universe looks the same no matter which way you look. These assumptions simplify the mathematics of cosmology enormously. They allow scientists to model the entire universe using relatively straightforward equations. Without the cosmological principle, the equations become vastly more complicated, and predictions become much harder to make. The principle has been remarkably successful, accurately describing many observations, but the KBC void represents a major violation of homogeneity. If the void is 2 billion light-years across with a 20% density deficit, that is huge in homogeneity. Even on cosmic scales, the void is not small compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling, we happen to live near the centre of this abnormal structure, which seems to contradict the idea that our location is unremarkable. Throughout history, science has progressively removed Earth from any special position. Copernicus showed Earth was not the centre of the solar system. Later observations showed the solar system was not the centre of the galaxy, and the galaxy was not the centre of anything. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the centre, but there is no centre because every location is equivalent. The void challenges that worldview. If we live inside an abnormally large underdense region, our location is unusual by definition. Voids are common in the universe, but most are smaller than the KBC void. Supervoids this large are rare, and finding ourselves in one raises questions about whether the cosmological principle truly holds or whether it is only approximately true on scales much larger than previously thought. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare, perhaps a 10 sigma statistical deviation. In a typical random realization of the universe's structure, you might not find one anywhere in the observable cosmos, yet we are in one. This suggests either we are incredibly lucky or the standard model is wrong about how structure forms. Defenders of the cosmological principle argue that the void does not actually violate the principle, because homogeneity only applies at scales of several hundred megaparsecs or larger. The void is about 600 megaparsecs across, which is right at the edge of where homogeneity is supposed to kick in. Maybe the universe is less smooth at those scales than we assumed. Alternatively, maybe the void is not as extreme as measurements suggest. Different observational techniques give somewhat different density contrasts for the void. Some studies find a 20% density deficit, others find closer to 10 or 15%. If the true deficit is on the lower end, the statistical rarity becomes less severe, though it remains a challenge for standard models. Confirming the void's exact properties requires more data, particularly deeper galaxy surveys that can map the void's extent and density profile with higher precision. Another defense is that we should not be surprised to find ourselves in an unusual location, because observers can only exist in certain types of environments. This is a weak anthropic argument. Perhaps intelligent life requires galaxies to form, and galaxies form preferentially in moderately dense regions, rather than in the densest clusters or the emptiest voids. If most observers live in mildly underdense regions, then finding ourselves in a slight void is not surprising. But this argument only works if the KBC void is not as extreme as it appears. A 20% deficit is more than mild, and it pushes the boundary of what the anthropic principle can explain away. The debate over the cosmological principle is not settled. Some researchers believe the void is real and significant, requiring either modifications to cosmology or acceptance that Earth occupies a genuinely unusual position. Others believe the void is an observational artifact or not as extreme as initially reported. Still others propose that the principle holds on even larger scales, and that the apparent violation is temporary. Future observations should help resolve this. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict or whether they are more common than expected. If big voids turn out to be frequent, the cosmological principle survives, but the standard model needs revision. If they are truly rare, we need to explain why we happen to live in one. Galaxies inside cosmic voids grow up in profound loneliness. Unlike galaxies in dense clusters that interact frequently with neighbours, void galaxies evolve in isolation, and this environmental difference shapes everything about them. Void galaxies tend to be smaller and dimmer than galaxies in filaments. They have lower masses, containing fewer stars and less overall matter, and many void galaxies are classified as dwarf galaxies, barely massive enough to hold onto their gas against the outward pressure from star formation. Their isolation means they rarely experience the galaxy mergers that are common in dense regions. Mergers are a primary driver of galaxy evolution, triggering bursts of star formation and feeding central black holes. Without mergers, void galaxies evolve more slowly and remain less developed. The star formation rate in void galaxies is generally lower than in cluster galaxies, but there is a surprising twist. While most void galaxies form stars slowly, a higher fraction of them are starburst galaxies, experiencing intense short-lived periods of rapid star formation. This seems paradoxical until you consider the gas content. Void galaxies are often unusually gas-rich, containing large reservoirs of neutral hydrogen that have not yet been converted into stars. In dense environments, interactions with neighbouring galaxies can strip away gas or trigger star formation, depleting the reservoir. In voids, galaxies retain their gas longer, and when star formation does ignite, perhaps triggered by internal processes rather than external interactions, there is plenty of fuel available. The result is an intense starburst that consumes gas rapidly before settling back into quiescence. The morphology of void galaxies also differs. Most are late-type spirals or irregular galaxies rather than elliptical galaxies. Elliptical galaxies form primarily through mergers, which are rare in voids. Without mergers, galaxies maintain their disk structures and spiral arms, and some void galaxies show remarkably undisturbed morphologies, with smooth disk profiles and regular rotation patterns. They have not been battered by interactions or gravitational tides from neighbours. This makes them excellent laboratories for studying how galaxies evolve in peaceful environments. Observations of void galaxies provide a baseline for comparison with the more chaotic evolution seen in dense regions. The dark matter halos around void galaxies are another interesting feature. Dark matter dominates the mass of every galaxy, forming a halo that extends far beyond the visible stars. In voids, these halos are subject to less external gravitational influence. They remain more spherical and undisturbed compared to halos in clusters, which often get stretched and distorted by tidal forces from neighbouring halos. The simpler halo structure in voids makes them easier to model and study. However, the lowest mass halos in voids face a challenge. Below a certain mass threshold, roughly corresponding to a circular velocity of 35 km per second, halos have too little gravity to retain gas efficiently. Star formation requires gas to cool and collapse, which happens more easily in deeper gravitational wells. The shallowest halos cannot form stars at all, and this explains why voids are not completely filled with tiny dwarf galaxies. Below a certain mass, halos exist but remain dark, containing only dark matter and no visible galaxies. One puzzling aspect of void galaxies is their chemical composition. Stars create heavy elements through nuclear fusion, and when they die, they release these elements into space. Subsequent generations of stars incorporate these elements, gradually enriching the galaxy's overall chemical composition. This process is called chemical evolution. Void galaxies, with their slower star formation rates, should have lower chemical enrichment compared to galaxies in dense regions. Observations confirm this to some extent. Void galaxies tend to have lower metallicities, meaning less abundance of elements heavier than helium, but the difference is not as large as expected. Some void galaxies show chemical abundances surprisingly similar to galaxies in normal environments. This suggests chemical evolution is more complex than simple models predict, perhaps involving gas flows in and out of galaxies that redistribute elements. The evolution of void galaxies over cosmic time is an active research area. By observing void galaxies at different distances, which corresponds to different times in the past, scientists can trace how these galaxies have changed. Early results suggest void galaxies have been relatively stable, evolving gradually without the dramatic transformations common in clusters. This stability makes them valuable for understanding the intrinsic processes that drive galaxy evolution without environmental complications. Future surveys with improved sensitivity will discover fainter void galaxies and trace their properties across billions of years of cosmic history. These observations will test whether our understanding of galaxy formation is complete, or whether void environments reveal processes we have missed. The KBC void is not the largest underdense region known. That distinction belongs to the Eridanus supervoid, discovered through its impact on the cosmic microwave background. Located in the constellation Eridanus, this void is roughly 1.8 billion light-years across, making it comparable in scale to the KBC void. What makes the Eridanus supervoid particularly intriguing is how it was found. Astronomers did not discover it by counting galaxies. They discovered it by noticing an unusually cold spot in the cosmic microwave background temperature map. This cold spot, about 10 degrees across on the sky, corresponds to a region where the microwave background is about 70 millionths of a degree cooler than average. That is much colder than typical fluctuations from the early universe. The cold spot, as it is called, was discovered by the Wilkinson Microwave Anisotropy probe in 2005. Its existence puzzled cosmologists because its size and temperature deficit are statistically unusual. Random fluctuations from the early universe should occasionally produce cold spots, but one this large and cold is rare, occurring in only about 2% of simulated universes. Some researchers initially proposed exotic explanations, including the possibility that it represented a collision between our universe and another universe in a multiverse. More prosaic explanations suggested it might be a random statistical fluke or an artifact of how the data was processed. But the cold spot persisted in multiple independent datasets, including observations from the Planck satellite. A more conventional explanation emerged when astronomers surveyed the galaxy distribution in the direction of the cold spot. They found evidence for a large underdense region roughly aligned with it. This void, later named the Eridanus supervoid, sits about 3 billion light-years away. Light from the cosmic microwave background passes through this void on its way to Earth. experiencing the integrated Sachs-Wolf effect. As the light traverses the expanding void, it loses energy, showing up as a temperature deficit. Calculations show that a void of the Eridanus supervoid's size and depth can account for about half of the observed cold spot temperature anomaly. The other half might come from a chance alignment with a cold fluctuation in the primordial cosmic microwave background, or it might indicate the void is larger and deeper than current measurements suggest. The Eridanus supervoid raises the same questions as the KBC void. How did such a large underdense region form? Is it consistent with standard cosmology, or does it require unusual initial conditions? The void's existence was predicted by the cosmic microwave background cold spot before it was confirmed by galaxy surveys, which gives researchers some confidence in its reality. But measuring its precise properties remains difficult because it is so distant. Galaxy surveys at that distance are less complete than nearby surveys. Many faint galaxies are missed, making it hard to quantify the exact density deficit. Current estimates place the deficit at about 20 to 30% compared to cosmic average, similar to the KBC void. If both the KBC void and the Eridanus supervoid are real, and as extreme as measurements suggest, it raises the likelihood that such voids are more common than standard cosmology predicts. Two large supervoids in the observable universe might still be consistent with lambda cold dark matter, if you allow for some statistical variance, but finding 3 or 4 would become increasingly difficult to explain. Future deep surveys will map the universe to even greater distances and discover more voids. The statistical distribution of void sizes and depths will test whether structure formation matches predictions. If large voids are common, it suggests either we misunderstand structure formation, or we live in an atypical part of the universe where large voids happen to cluster. Neither option is comfortable. The Eridanus supervoid also demonstrates that voids affect observations in measurable ways. The temperature deficit they create in the cosmic microwave background is small but detectable. The velocity fields they generate are observable through bulk flow measurements. These effects are not just theoretical predictions, they are real phenomena that astronomers can study. This gives researchers hope that the mysteries surrounding the KBC void and the Hubble tension can eventually be resolved through better observations. If voids systematically affect measurements in known ways, those effects can be corrected for or modelled. The challenge is obtaining sufficient data to characterize the void structure of the universe accurately. One thing is clear: the universe contains more large voids than early cosmological models anticipated. Whether this reflects the rarity of our cosmic neighbourhood or inadequacies in our models remains an open question. The cosmic microwave background provides other clues about void structure. The temperature fluctuations we observe encode information not just about the early universe, but also about the structure light encounters during its journey to us. Sophisticated analysis techniques can separate these contributions. The primordial fluctuations tell us about conditions 380,000 years after the Big Bang. The integrated Sachs-Wolf effect tells us about structure formation since then. By mapping cold spots in the cosmic microwave background and correlating them with galaxy surveys, astronomers can identify voids even at distances where direct galaxy counts are difficult. This technique has revealed numerous large voids throughout the observable universe. Each discovery adds to the statistical sample, helping determine whether supervoids like the KBC void and Eridanus supervoid are exceptional rarities or merely the largest members of a more common population. The cold spot phenomenon also highlights the interconnected nature of cosmic observations. What appears as a temperature anomaly in one wavelength regime corresponds to an underdense region, visible in galaxy surveys at optical wavelengths. Both observations trace the same underlying structure, the cosmic web of filaments and voids shaped by billions of years of gravitational evolution. By combining observations across multiple wavelengths and techniques, astronomers build a more complete picture of cosmic structure. The Eridanus supervoid sits too far away for detailed study of individual galaxies within it. At 3 billion light-years distance, only the brightest galaxies are visible, and measuring their velocities with precision is challenging. This limits what we can learn about the void's internal dynamics. The KBC void, being much closer, offers a unique opportunity for detailed characterization. We can measure galaxy velocities, map density profiles, study individual void galaxies, and test predictions about void behaviour with higher precision than possible for distant voids. This proximity makes the KBC void simultaneously a blessing and a curse. A blessing because we can study it in detail, a curse because being inside it potentially biases all our cosmological measurements. If we lived outside the void, we could study it objectively without worrying about how it affects our measurements of cosmic expansion, dark energy, or other fundamental parameters. But we cannot choose our location. We can only work with what we have and try to account for biases as best we can. The term Hubble bubble has emerged to describe a troubling observational pattern. When astronomers measure the Hubble constant using nearby objects like supernovae within about 2 billion light years, they get higher values around 73 km per second per megaparsec. When they use objects farther than 2 billion light years or rely on cosmic microwave background data, they get lower values around 67 km per second per megaparsec. The boundary at roughly 2 billion light years is suspiciously close to the edge of the KBC void. This has led researchers to propose that measurements within the void are affected by its presence, creating a bubble of biased observations. Only by looking beyond the bubble can we see the universe's true expansion rate. This hypothesis makes a clear prediction. The measured Hubble constant should vary with distance. Nearby measurements should show the highest values. As you look farther out, approaching and crossing the void's edge, the measured value should decline toward the cosmic average. Beyond 2 billion light years, it should stabilize at the lower value. This is exactly what recent observations are beginning to show. Studies using supernovae at various distances find that the inferred Hubble constant decreases with redshift. The trend is not yet definitive because measuring distances to very distant supernovae is challenging, and uncertainties are large, but the direction of the trend matches predictions from the Hubble bubble hypothesis. If the bubble is real, it creates a significant problem for cosmology. Most measurements of the local expansion rate necessarily use nearby objects because those are the only ones we can observe in sufficient detail. Distant objects are fainter and harder to characterize precisely. This means our most reliable local measurements are exactly the ones most affected by the void. We are trapped inside the bubble, unable to step outside our local environment to see what the universe truly looks like. It is like trying to determine Earth's climate by only measuring the temperature inside a heated building. You can make very precise measurements, but they do not represent the global average. Breaking out of the bubble requires observing objects beyond 2 billion light years with comparable precision to nearby objects. This is technologically challenging but becoming possible. Space telescopes like the James Webb Space Telescope can observe distant supernovae with unprecedented detail. Ground-based observatories with enormous mirrors and advanced instruments are discovering quasars and other bright objects at extreme distances. These distant probes offer a window into the universe outside the bubble. Early results suggest the far universe expands at the rate predicted by the cosmic microwave background, consistent with the bubble hypothesis, but the data are still limited. More observations are needed to confirm the trend and establish whether it fully resolves the Hubble tension. The bubble concept also applies to other measurements. Bulk flow observations show significant motions out to about 300 million light years, but appear to decline at larger distances. This is consistent with the void creating a local velocity field that dissipates as you approach the void's edge. The baryon acoustic oscillation measurements show discrepancies primarily at low redshift, again suggesting local effects. Multiple independent lines of evidence point to the same conclusion. Our local environment within about 2 billion light years differs systematically from the universe at large. We live in an island of unusual properties surrounded by a more typical cosmos. Accepting the Hubble bubble hypothesis requires accepting that many of the measurements we use to understand the universe are biased by our location. This is philosophically uncomfortable. Scientists prefer to believe their observations are representative of universal truths rather than local accidents. But the evidence increasingly suggests we cannot escape our local bias without looking far enough away that the void's influence fades. Future surveys that probe the universe beyond 2 billion light years will be crucial for confirming whether the bubble is real and whether it fully explains the Hubble tension. If it does, cosmology can breathe a sigh of relief. The standard model works fine, we just happen to be measuring from a weird spot. If the tension persists even at large distances, new physics will be required. The The KBC void's existence has led some scientists to question whether gravity itself needs revision. The standard theory of gravity is Einstein's general relativity, formulated in 1915. It has passed every test thrown at it for over a century, from predicting the bending of light around massive objects to explaining the orbital decay of binary pulsars, and general relativity forms the foundation of modern cosmology. But the KBC void challenges this foundation in unexpected ways. If the void is too large and too deep to arise naturally in simulations based on general relativity and lambda cold dark matter, perhaps gravity does not work exactly as Einstein predicted on the larger scales. Some scientists propose modifying gravity rather than accepting we live in a statistically improbable location. Modified Newtonian dynamics, or MOND, is the most prominent alternative gravity theory, proposed in 1983 by physicist Mordechai Milgram. MOND suggests that gravity behaves differently when accelerations are extremely small, below a certain threshold. At high accelerations like those on Earth or in the inner solar system, gravity follows Newton's laws and Einstein's corrections exactly. But at the tiny accelerations relevant for galaxy outskirts and cosmological scales, gravity becomes stronger than general relativity predicts. This modification was originally proposed to explain galaxy rotation curves without invoking dark matter. Galaxies spin faster than visible matter can account for, so either there is invisible dark matter providing extra gravity, or gravity itself is stronger at large distances. MOND has struggled to explain many cosmological observations, but it performs better than expected at explaining some features of the cosmic web. In MOND cosmology, structures form more efficiently because the enhanced gravity on large scales pulls matter together more effectively. This produces richer superclusters and deeper voids compared to standard gravity. Computer simulations using MOND gravity naturally create voids as large as the KBC void without requiring unusual initial conditions, and the statistical improbability disappears. The void becomes an expected consequence of how structure forms under modified gravity. This is an attractive feature because it resolves the tension between observations and theory without invoking extreme luck. However, MOND faces serious challenges. It struggles to explain the cosmic microwave background temperature fluctuations, which standard cosmology explains beautifully using general relativity. MOND also cannot easily account for gravitational lensing observations, where massive galaxy clusters bend light from background galaxies. The amount of lensing observed requires more gravity than visible matter, plus MOND's modification can provide. Suggesting dark matter is still needed. Some researchers have developed hybrid models that combine MOND with a small amount of dark matter, typically in the form of neutrinos. These models, called neutrino hot dark matter cosmologies, can explain both the cosmic microwave background and the enhanced structure formation seen in the cosmic web. Another class of modified gravity theories involves changing how gravity propagates over large distances rather than changing its strength. These theories, collectively called modified gravity theories, introduce additional fields or higher dimensional effects that alter gravitational dynamics on cosmological scales while preserving general relativity successes on smaller scales. Some of these theories predict that gravity becomes effectively stronger in low-density regions like voids, which would make large voids easier to form. Testing these theories requires precise measurements of how matter moves in voids versus dense regions. If the velocity patterns deviate from general relativity's predictions, it could indicate modified gravity at work. The debate between modified gravity and standard cosmology, with a statistically unlikely void, remains unresolved. Proponents of modified gravity argue that repeatedly finding structures that are too large or too rare according to standard models indicates the models are wrong. They point to the KBC void, the Shapley supercluster, the Sloan Great Wall, and other enormous structures as evidence that structure formation is more vigorous than lambda cold dark matter predicts. Defenders of standard cosmology argue that modified gravity theories have their own problems, and that invoking them to solve one puzzle often creates new puzzles elsewhere. They prefer to accept that we live in an unusual location rather than overthrowing a century of successful gravitational physics. Future observations should help settle this debate. If large voids and extreme structures turn out to be more common than currently thought, modified gravity becomes more appealing. If they remain rare, the standard model survives but leaves us with the uncomfortable conclusion that Earth occupies a special location. Either way, the KBC void has become a battleground where fundamental physics is being tested. Galaxies are not stationary. They move through space in response to gravity from surrounding structures, and these motions are called peculiar velocities because they are peculiar to each galaxy, distinct from the overall cosmic expansion. In standard cosmology, peculiar velocities should be relatively small and random on large scales. Nearby galaxies might move at a few hundred kilometers per second due to local gravity, but when you average over volumes hundreds of millions of light-years across, those peculiar velocities should largely cancel out. The average motion, called bulk flow, should be close to zero. This is what homogeneity predicts. If the universe is truly uniform on large scales, there should be no coherent large-scale flows because there are no large-scale gravitational gradients to drive them. Observations tell a different story. Measurements of galaxy velocities using multiple techniques show significant bulk flows extending to distances of 200 to 300 million light-years. These flows reach velocities of 400 kilometers per second or more, far higher than standard cosmology predicts. For such large scales, the flows are coherent, meaning galaxies across huge volumes are all moving in roughly the same direction. This suggests the presence of large-scale structure producing gravitational gradients that pull matter in specific directions. The KBC void is exactly the kind of structure that could produce such flows. Material within the void is accelerating outward toward denser regions beyond the void's edges, and this creates a bulk flow pointing away from the void center. Measuring bulk flows is challenging because it requires accurate distance estimates for many galaxies. Redshift alone is not enough because it mixes cosmic expansion with peculiar velocity. You need independent distance measurements that do not rely on redshift. Techniques like Tully-Fisher, relations for spiral galaxies, and fundamental plane relations for elliptical galaxies provide these distances. By comparing the distance-based velocity to the redshift-based velocity, astronomers can extract the peculiar velocity. Compiling measurements for thousands of galaxies allows mapping the large-scale velocity field. The Cosmic Flows project has done exactly this, creating the most detailed maps of bulk flows to date. The observed bulk flows match predictions from models that include the KBC void. When researchers simulate how galaxies should move if they are inside a large underdense region surrounded by overdense shells, the predicted velocities and flow patterns closely match observations. The flows are strongest near the void edges where the density gradient is sharpest. They are directed outward from the underdensity toward the surrounding filaments. The magnitude of the flows depends on the void's depth and size. A 20% density deficit extending 1 billion light-years produces flows of about 400 kilometers per second, exactly what is observed. This agreement is striking and provides strong support for the void hypothesis. Standard cosmology without a void struggles to explain these flows. Simulations based on lambda-cold dark matter predict bulk flows should decline rapidly with scale. By the time you average over 200 million light-years, bulk flows should be under 100 kilometers per second. The observed flows are 4 times larger. You can increase the predicted flows by assuming more structure than typical, but that requires invoking rare density fluctuations, which brings back the same statistical improbability issue that the void represents. Either way, the observations point to more structure on large scales than standard models comfortably predict. Some cosmologists view this as evidence that lambda-cold dark matter is missing something, either in its treatment of dark matter, dark energy, or the gravitational physics governing structure formation. Alternative theories, like modified gravity, naturally predict stronger bulk flows because they enhance structure formation. In Mond cosmology, for example, the effective gravitational strength on large scales is higher, creating deeper potential wells and stronger flows. The observed bulk flows are consistent with predictions without requiring statistically unlikely structures. This has led some researchers to favour modified gravity as a more natural explanation for both the KBC void and the associated bulk flows. However, modified gravity has other difficulties, so the debate continues. Upcoming surveys will measure bulk flows at even larger distances and with greater precision. If flows remain strong beyond 300 million light-years, it would further challenge standard cosmology. If they decline as expected, it would suggest the KBC void is an isolated feature, rather than indicative of systematic problems with the model. The bulk flow observations underscore a theme emerging throughout this story. our local cosmic environment is more dynamic and structured than simple homogeneous models assume. The universe on large scales may not be as smooth as the cosmological principle requires. Whether this means we live in an unusual location, or whether it means our models need revision, depends on how these observations develop. The KBC void and its associated flows are at the centre of this unfolding story. The velocity field within the void is not uniform. Close to the void centre, the outflow is rapid. Farther from the centre but still within the void, the outflow is slower. Beyond the void's edge, the peculiar velocities might even reverse as matter falls back toward the denser filaments. This creates a complicated velocity profile that varies with distance. When astronomers measure the Hubble constant using supernovae at different distances, they are sampling this varying velocity field. If most of their supernovae lie within the void, which they do, because we deliberately avoid using extremely distant supernovae due to other complications, the measurement gets boosted by the outflow. The farther out you measure, the less the void affects the result. This predicts that the Hubble constant should appear to decrease with distance, and recent observations confirm exactly that trend. Modelling these effects requires careful calculation. Scientists must estimate the void's size, depth, and density profile, then calculate the gravitational potential it creates. That potential determines how fast material flows outward at each radius. The calculations show that a void roughly 1 billion light-years in radius, with a 20% density deficit, can easily produce the observed velocity anomalies. The match between predictions and observations is good enough that many researchers find the void explanation compelling. The velocity field also affects other observations: the dipole in the cosmic microwave background, the pattern where one hemisphere appears slightly warmer and the other slightly cooler, results from our motion through space relative to the rest frame defined by the cosmic microwave background. This motion is the sum of all local peculiar velocities. The Milky Way's velocity relative to the cosmic microwave background is about 627 km per second. This high speed indicates strong gravitational gradients in our vicinity, exactly what you expect from being near a large underdense region. If we lived in a typical region with average density, our peculiar velocity would be much smaller, maybe 100 or 200 km per second at most. The fact that we are moving so fast is itself evidence for the void. The velocity is consistent with the void hypothesis and would be difficult to explain without it. This makes our motion a key piece of evidence in the debate over whether the KBC void exists and whether it affects our measurements. The motion of the local group, and by extension the Milky Way, is influenced by multiple attractors. The Virgo cluster pulls us toward it at about 250 km per second. The Great Attractor, a massive concentration of galaxies behind the Virgo cluster, adds its own pull. The Shapley supercluster, located about 650 million light-years away, is the most massive structure in our region and exerts gravitational influence even at that distance. All these attractors combine with the void's outward push to create our net peculiar velocity. Disentangling these components requires careful modelling of the mass distribution in our cosmic neighbourhood. The Cosmic Flows project has made significant progress in mapping these flows and identifying the various contributors. Their work shows that the void plays a major role in shaping local velocities, confirming its importance for understanding our cosmic environment. Dark energy is accelerating the universe's expansion, and that acceleration has dire implications for the far future. As space expands faster over time, structures that are not gravitationally bound together will drift apart and eventually lose all contact. This process is already happening, but it will intensify over the coming billions and trillions of years. Voids will expand faster than the universe as a whole because they contain less matter to resist the expansion. The filaments surrounding voids will thin out as galaxies within them are stretched farther apart. Eventually, even neighbouring superclusters will lose causal contact as space between them expands faster than light can cross. The universe's fate is increasing isolation, with structures becoming islands separated by ever-expanding voids. For galaxies within voids, this isolation will be profound. Currently, galaxies in the KBC void can still see the surrounding filaments and clusters in the distance. Light from those structures reaches us after travelling for billions of years, but as dark energy drives accelerating expansion, light from increasingly distant objects will never reach us. The cosmic horizon, the boundary beyond which light cannot reach us before the universe expands too much, will shrink over time. Objects currently visible will fade from view as their light gets redshifted into invisibility. Galaxies deep within voids will find themselves in increasingly empty skies, with fewer and fewer neighbours visible. The cosmic microwave background radiation will become cooler and dimmer as its photons stretch to longer wavelengths. Eventually it will become undetectable. This raises a disturbing question for future civilizations. If a civilization arises in a void galaxy billions of years from now, what will they be able to learn about the universe? Their sky will be nearly empty except for their local group of galaxies. The cosmic microwave background will be too faint to detect. There will be no evidence of the Big Bang, no distant galaxies to measure cosmic expansion, no supernovae to trace the acceleration. They will be cosmologically isolated, unable to observe the larger universe because light from beyond their immediate vicinity cannot reach them. Such civilizations might conclude they live in a static island universe surrounded by empty space, never suspecting the vaster cosmos beyond their horizon. This scenario, sometimes called the dark future, is the inevitable consequence of accelerating expansion. Even within our own void, the long-term future looks lonely. The Milky Way and Andromeda will merge in about 4 billion years, forming a giant elliptical galaxy sometimes called Milkomeda. This merged galaxy will be the dominant structure in our local group, but the local group itself will become increasingly isolated. Other nearby groups like the Leo Spur or the Virgo cluster will recede beyond our cosmic horizon within tens of billions of years. Milkomeda will find itself essentially alone in an expanding void. Star formation will gradually cease as gas is consumed or expelled, and the galaxy will fade, containing only old red stars and eventually just white dwarfs, neutron stars and black holes. The night sky will darken as fewer stars remain active. On even longer timescales, trillions of years into the future, stars will become rare as their fuel is exhausted. Galaxies will consist mainly of dead stellar remnants slowly evaporating into space through gravitational interactions. Black holes will dominate, slowly growing by accreting whatever material remains. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that causes them to lose mass over incomprehensibly long time scales. The final state of the universe will be a diffuse sea of particles and radiation, expanding forever into darkness. Voids will have consumed everything, with the last remnants of structure dissipating into the void's infinite expanse. This bleak future is billions of years away and depends on dark energy continuing to accelerate expansion. If dark energy changes in strength or sign, the future could be different, but current observations suggest dark energy is a cosmological constant, unchanging and unrelenting. If so, the universe's ultimate fate is void domination. The cosmic web we observe today, with its intricate filaments and clusters, is a temporary phase. The true long-term structure of the universe is emptiness punctuated by isolated islands of matter that grow ever more remote from each other. We live in an unusual time when the universe still has rich structure, and when voids are features rather than the dominant reality. Billions of years hence, voids will be everything. We are inside a cosmic hole 2 billion light-years wide. This is not metaphor or speculation, this is observation. The KBC void is real, its effects are measurable, and its existence challenges fundamental assumptions about cosmology. Whether it explains the Hubble tension, whether it requires modified gravity, whether it makes us unusually positioned in the universe, these questions remain open. But one thing is certain, the universe is far stranger than we imagined, and our place within it is more unusual than we ever suspected. The discovery of the KBC void forces us to confront uncomfortable truths about scientific observation. Every measurement we make is coloured by our location, and if that location is unusual, our measurements might not represent cosmic averages. This does not mean our observations are wrong, but it means they require careful interpretation. The void teaches us humility about what we can know from a single vantage point. The implications extend beyond cosmology into philosophy. For centuries, science has worked to remove humanity from any privileged position in the cosmos. We're not at the centre of the solar system, not at the centre of the galaxy, not at the centre of anything. The cosmological principle codifies this idea, stating that the universe should look the same from any location. Finding ourselves in a cosmic void challenges that principle, suggesting our location may be unusual after all. This raises profound questions. If we live in an unusual location, are other civilizations similarly situated? Does the structure of the cosmic web influence where intelligent life arises? Could it be that most observers in the universe inhabit voids simply because voids offer more stable environments for life to develop? These questions remain speculative, but they illustrate how the discovery of the void opens new avenues of inquiry. The void also reminds us that the universe is not designed for our comprehension. We evolved to navigate a world of human scales, not cosmic ones. Our intuitions about space, time, and structure break down when we try to apply them to regions billions of light years across. The void defies our expectations precisely because it operates on scales so far removed from daily experience. Understanding it requires mathematical models and careful observation rather than intuition. Looking forward, the study of cosmic voids will continue to be a major focus of observational cosmology. New surveys with improved sensitivity and larger sky coverage will map voids in unprecedented detail. The Dark Energy Spectroscopic Instrument, the Vera Rubin Observatory, and future space missions will discover thousands of voids at various distances and sizes. Each void provides an independent test of cosmological models, and each measurement brings us closer to understanding whether the KBC void is a rare anomaly or part of a broader pattern we have yet to fully grasp. The void also offers opportunities for testing fundamental physics. By measuring how matter moves in voids versus dense regions, scientists can test whether gravity works as general relativity predicts, or whether modifications are needed. By mapping void shapes and evolution, researchers can constrain the properties of dark energy and dark matter. By studying galaxies in voids, astronomers can understand how environmental factors shape galaxy evolution. The void is not just a problem for cosmology, it is a laboratory for exploring physics at its most fundamental level. What becomes clear from all this is that the universe is far more complex and structured than early cosmologists imagined. The smooth, homogeneous cosmos of textbook models is an idealization that breaks down when we look closely at specific regions. Real structure is messy, inhomogeneous, and full of surprises. The cosmic web with its filaments, clusters, and voids represents the actual architecture of the universe, and understanding this architecture is essential for understanding cosmic evolution. We are cosmic castaways, drifting through a desert of space, measuring a universe that may not be what it seems. The void around us shapes every observation we make and every conclusion we draw. Whether future discoveries confirm the void as the solution to cosmology's problems or reveal deeper mysteries remains to be seen. But one thing is undeniable: we are living in one of the strangest places in the observable universe, and that fact alone should make us question everything we think we know about the cosmos. The journey to understand the KBC void is far from over. Each new observation raises new questions, each answer leads to deeper mysteries, and the full implications of living inside a cosmic hole are still unfolding. As technology improves and surveys map the universe with greater precision, we will learn whether the void is friend or foe to our cosmological models. We will discover whether other supervoids exist, and whether they too harbour galaxies with observers wondering about their place in the cosmos. The void forces us to reconsider fundamental assumptions. The cosmological principle, which states the universe should look the same from any location, may require revision. Perhaps the principle only holds on scales larger than we currently observe. Perhaps it holds statistically across many regions but allows for rare exceptional locations like ours. Or perhaps it simply fails, and the universe is more inhomogeneous than we thought. These philosophical questions connect to practical ones. If our measurements are biased by our location, how do we correct for that bias? Do we need to wait for observations from regions billions of light years away to understand the true cosmic expansion rate? Or can we model the void's effects accurately enough to extract universal truths from local observations? The answers will determine how cosmology proceeds in the coming decades. The void also reminds us that scientific progress requires humility. For centuries, we believed Earth was at the center of everything. Then we learned we orbit the Sun, which orbits the galaxy, which moves through space with no special position. The cosmological principle enshrined this idea that we occupy a typical, unremarkable location. The KBC void challenges that assumption, suggesting our location may be unusual after all. This does not mean we have returned to geocentrism or any other outdated worldview. it means the universe is complicated and simple generalizations sometimes fail. We must remain open to unexpected discoveries even when they contradict cherished principles. The void teaches us to hold our assumptions lightly and let observations guide our understanding, rather than forcing observations to fit preconceived notions. Looking beyond cosmology, the void raises questions about life in the universe. If voids provide more stable environments than dense regions, perhaps most civilizations rise in voids. The isolation and reduced frequency of catastrophic events might favor the development of complex life. If so, finding ourselves in a void would not be surprising from an anthropic perspective. We could only ask these questions from a location where conditions allowed us to evolve. Alternatively, if voids are inhospitable due to low metallicity and reduced star formation, civilizations might be rare in voids. The fact that we find ourselves here would then be a statistical fluke. One more layer of cosmic unlikeliness added to the already improbable chain of events that led to human existence. We cannot yet answer these questions, but the void adds a new dimension to the search for life beyond Earth. For now, we stand at the edge of understanding, peering into the void that surrounds us and wondering what it means. The universe has revealed itself to be stranger than we imagined, and our location within it more peculiar than we ever suspected. We are inside a cosmic hole, measuring the universe from the outskirts, and only time will tell what truths we uncover from this unlikely vantage point. The KBC void's existence forces a complete re-evaluation of how we conduct precision cosmology. Every major cosmological parameter we measure, from the Hubble constant to the matter density to the properties of dark energy, depends on observations that could be systematically biased by our location inside a large underdense region. This realization has sparked a renaissance in thinking about systematic errors and observational biases. Consider the cosmic distance ladder, the series of overlapping measurement techniques that allow us to determine distances to galaxies across the universe. The ladder starts with parallax measurements to nearby stars, moves to variable stars like Cepheids in more distant galaxies, then to Type Ia supernovae even farther out. Each rung calibrates the next, building up to cosmological distances where we can measure the expansion of the universe. But if we live in a void, every rung of that ladder measured from within our local region could be systematically affected. Feed calibrations might be biased if local conditions differ from those in typical regions. Supernova measurements within the void necessarily sample an unusual velocity field. The accumulated systematic error could be larger than the statistical uncertainties astronomers have worked so hard to minimize. This problem extends to other techniques as well. Gravitational lensing, where massive objects bend light from background sources, provides independent constraints on cosmic structure and expansion. But lensing measurements depend on knowing the distances to both the lens and the background source. If void effects alter those distance estimates, lensing measurements become less reliable. Cosmic microwave background observations seem immune to void effects because they probe the universe 380,000 years after the Big Bang, long before voids formed. But even here, subtleties arise. The integrated Sachs-Wolf effect, where cosmic microwave background photons gain or lose energy, passing through evolving structures, is affected by voids. Large voids leave cold spots in the cosmic microwave background, and if we are looking through the KBC void from inside, that could create directional biases in how we interpret cosmic microwave background data. The response from the cosmology community has been to develop void-corrected analysis methods. These approaches attempt to model the void's effects and remove them from observations, extracting the underlying cosmic signal. The challenge is that modelling requires knowing the void's properties precisely, including its exact size, depth, density profile, and velocity field. Uncertainties in any of these translate to uncertainties in the corrections. Some researchers advocate measuring the Hubble constant using only galaxies beyond the void's edge, avoiding the contaminated region entirely. This approach has the advantage of simplicity, but the disadvantage of reduced sample size. Distant galaxies are harder to observe, fewer suitable targets exist, and measurement uncertainties increase. The trade-off between avoiding systematic error and maintaining statistical precision is not straightforward. Another approach involves comparing measurements from different directions. If the void has a definite edge, observations in different directions should show varying levels of bias depending on whether the line of sight passes through the void's center, edge, or beyond. By mapping directional variations, astronomers can characterize the void's shape and extent while simultaneously correcting for its effects. This technique requires enormous data sets covering the full sky, which upcoming surveys will provide. The void also affects tests of general relativity and alternative gravity theories. Many tests rely on measuring how gravity affects light and matter on cosmological scales, but if local measurements are contaminated by void effects, distinguishing between standard gravity in an unusual location and modified gravity in a typical location becomes difficult. The degeneracy between environmental effects and fundamental physics modifications complicates efforts to test gravity. Breaking this degeneracy requires combining multiple types of observations. If void effects are purely gravitational, following standard general relativity in an underdense environment, the various observational signatures should all be consistent with each other in a predictable way. If modified gravity is involved, discrepancies should emerge because different types of observations would deviate from expectations in different ways. The coming decade will be critical for resolving these issues. Multiple independent surveys using different techniques will either converge on a consistent picture or reveal persistent discrepancies. If the void hypothesis is correct and we can model it accurately, all observations should become consistent once void corrections are applied. If discrepancies remain, it indicates either our void model is incomplete or additional physics beyond standard cosmology is required. The precision measurements enabled by future instruments will also test whether the void is as uniform as currently assumed. Current observations treat the void as having a smooth, slowly varying density profile. But what if the interior structure is more complex? Smaller voids within the larger void, or filaments crossing through it, could create localized regions with different properties. Mapping this fine structure requires observing many galaxies throughout the void's interior, which has not been possible until now. The Dark Energy Spectroscopic Instrument will observe millions of galaxies within the KBC void's volume, providing unprecedented detail about its internal structure. If the void is indeed smooth and uniform, the data will confirm current models. If unexpected structure appears, models will need revision. Either outcome advances our understanding, but the latter would be more exciting because it would indicate our picture of the void is oversimplified. Another critical test involves searching for other examples of galaxies living in supervoids and comparing their cosmological measurements to ours. If other regions show similar systematic biases consistent with void effects, it strengthens the case that location matters. If other void dwellers show different biases or no biases, it suggests the KBC void may not explain our observations after all. Finding and characterizing other supervoids in detail is a major observational challenge, but one that next-generation surveys are designed to meet. The void's impact on cosmology extends even to exotic tests. For example, searches for variations in fundamental constants often look for changes across cosmic time or space. If constants vary, the spectral lines of atoms in distant galaxies should show subtle shifts compared to laboratory measurements. But such searches assume the comparison sample of distant galaxies represents typical cosmic conditions. If those galaxies are also in voids or other unusual environments, the comparisons become less meaningful. Similarly, tests of isotropy, whether the universe looks the same in all directions, could be affected by the void. Large voids create directional asymmetries in galaxy counts, peculiar velocities, and expansion rates. These asymmetries might masquerade as fundamental violations of isotropy when they are actually environmental effects. Distinguishing true violations of cosmological symmetries from local environmental contamination requires careful analysis. The void thus serves as a cautionary tale for observational cosmology. Precision measurements alone are not enough if systematic errors dominate. Understanding our cosmic environment and accounting for its effects is as important as building better instruments and collecting more data. The field has entered an era where environmental corrections are essential components of cosmological analysis rather than optional refinements. This shift represents both a challenge and an opportunity. The challenge is that every measurement must now be scrutinized for possible void contamination, adding layers of complexity to analysis. The opportunity is that studying the void itself provides new ways to test cosmology and fundamental physics. The same feature that complicates some measurements enables others, and the richness of information contained in void structure offers multiple pathways to understanding. Understanding the KBC void requires sophisticated observational techniques that have only recently become available. Galaxy surveys form the backbone of void detection, but not all surveys are equal. Different wavelengths reveal different populations of galaxies, and different distance indicators provide complementary information. The convergence of multiple techniques has allowed astronomers to map the void with increasing confidence. Optical surveys like the Sloan Digital Sky Survey revolutionized our understanding of large-scale structure by systematically measuring redshifts for millions of galaxies. The survey used a dedicated telescope at Apache Point Observatory in New Mexico to photograph the sky and identify candidate galaxies, then followed up with spectroscopic observations to measure each galaxy's redshift. This provided three-dimensional positions for galaxies spanning billions of light-years. The resulting maps clearly showed the cosmic web of filaments and voids. But optical surveys have limitations. Dust in the plane of the Milky Way obscures galaxies in certain directions, creating zones of avoidance where galaxy counts are incomplete. Optical light is also scattered and absorbed by dust in distant galaxies themselves, potentially making them appear fainter or causing them to be missed entirely. These effects can bias density measurements, potentially making voids appear deeper than they truly are or making dense regions appear less dense. Infrared surveys address these issues. Infrared light penetrates dust more effectively than visible light, allowing astronomers to see galaxies that would be obscured optically. The 2-micron all-sky survey, which provided crucial data for the KBC void discovery, operated in near-infrared wavelengths. By comparing infrared galaxy counts to optical counts, researchers can assess how much dust extinction affects their observations and correct for it. The combination of optical and infrared data provides more robust density measurements than either technique alone. Radio surveys add another dimension. Neutral hydrogen gas emits radio waves at a characteristic frequency of 1420 MHz. Mapping this emission reveals the distribution of gas in and around galaxies. In voids, where galaxies are rare, the diffuse intergalactic medium can sometimes be detected through its hydrogen emission. Radio surveys also excel at detecting dwarf galaxies that might be too faint to appear in optical surveys. Distance measurements beyond redshift are critical for understanding the void's dynamics. Redshift tells you how fast a galaxy is receding, which combines cosmic expansion with peculiar velocity. To separate these components, you need an independent distance estimate. The cosmic distance ladder employs multiple methods calibrated against each other. For nearby galaxies, Cepheid variable stars serve as standard candles. These stars pulsate with periods that correlate with their intrinsic brightness. By measuring the pulsation period and apparent brightness, astronomers calculate distance. Type Ia supernovae work at larger distances. These exploding stars reach a predictable peak brightness, making them excellent distance indicators out to billions of light-years. The Tully-Fisher relation provides another method for spiral galaxies, correlating rotation speed with luminosity. Faster rotating galaxies are more luminous, so measuring rotation speed allows distance estimates. The fundamental plane relation does something similar for elliptical galaxies, using relationships between size, surface brightness, and velocity dispersion. Each method has systematic uncertainties, but by cross-calibrating multiple techniques, astronomers achieve distance measurements accurate to a few percent. This precision is essential for detecting the subtle velocity anomalies associated with the void. Future surveys will dramatically improve our knowledge of void structure. The Dark Energy Spectroscopic Instrument began operations in 2021 and is conducting the largest redshift survey ever attempted. Over 5 years, it will measure redshifts for 35 million galaxies, creating an unprecedented three-dimensional map of cosmic structure. This vast dataset will reveal voids throughout the observable universe, allowing statistical studies of void properties. The Vera Rubin Observatory, scheduled to begin operations soon, will conduct the Legacy Survey of Space and Time, photographing the entire visible sky every few nights for 10 years. This survey will discover billions of galaxies and track how they change over time. The time domain aspect is particularly valuable for supernova studies. By detecting supernova shortly after explosion and following their evolution, Rubin Observatory will provide distance measurements throughout the observable universe, testing whether the Hubble constant varies with distance as the void hypothesis predicts. The Euclid Space Telescope, launched by the European Space Agency, is mapping the geometry of the universe by observing billions of galaxies across cosmic time. Its combination of visible and infrared cameras provides deep, sharp images across large areas of sky. Euclid's measurements of weak gravitational lensing, where massive structures subtly distort the shapes of background galaxies, will map dark matter distribution, including in voids where optical galaxy counts are sparse. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will complement these efforts with even more sensitive infrared observations. Its wide field of view and deep sensitivity will discover faint galaxies missed by current surveys, improving our senses of galaxies in underdense regions. The Square Kilometre Array, a next-generation radio telescope under construction, will map neutral hydrogen across cosmic time with unprecedented sensitivity. This will reveal the gas content of voids and trace how matter flows between voids and filaments. Together, these facilities represent a golden age for observational cosmology. Within the next decade, we will have multiple independent measurements of void properties from different wavelengths and techniques. If the measurements converge on a consistent picture, our confidence in the void's existence and properties will solidify. If discrepancies emerge, they may point toward new physics or reveal systematic errors in current methods. The James Webb Space Telescope has already begun contributing to void studies. Its infrared sensitivity allows observations of distant galaxies with unprecedented detail. Early results include precise distance measurements to Cepheid variables in galaxies several tens of millions of light-years away, refining the cosmic distance ladder. These measurements help calibrate the expansion rate at various distances, testing whether the Hubble constant changes with distance as expected if we live in a void. Webb's spectroscopic capabilities also allow detailed studies of galaxy properties. By measuring the chemical composition, star formation rate, and gas content of void galaxies, astronomers can test whether these galaxies evolve differently than galaxies in dense regions. Early observations confirm that void galaxies tend to be gas-rich and less chemically evolved, consistent with predictions from simulations. Gravitational wave astronomy offers an entirely new way to measure cosmic expansion. When black holes or neutron stars merge, they emit gravitational waves that carry information about the distance to the merger. If the merger can be associated with an electromagnetic counterpart that provides a redshift measurement, the combination yields a Hubble constant measurement independent of the traditional distance ladder. These standard sirens, as they are called, are immune to many systematic errors affecting other methods. As gravitational wave detectors improve and more mergers are detected, standard sirens will provide critical cross-checks on traditional expansion rate measurements. If standard siren measurements show the same distance-dependent variation as supernova measurements, it will strongly support the void hypothesis. If they do not, it will suggest the Hubble tension has a different origin. The coming decade will likely resolve the questions surrounding the KBC void. Either observations will confirm the void explains the Hubble tension and other anomalies, allowing cosmology to proceed with confidence in the standard model, or they will reveal deeper mysteries requiring new physics. The accumulated data from multiple surveys and techniques will provide the statistical power to distinguish between competing explanations. We stand on the threshold of answers that have eluded cosmologists for over a decade. The discovery that we might live inside a cosmic void touches on deep philosophical questions about observation, knowledge, and the nature of scientific truth. These questions go beyond cosmology into epistemology, the study of how we know what we know. If our location significantly biases our observations, what does that mean for the scientific enterprise? Throughout history, humans have struggled with the question of whether we occupy a special place in the cosmos. Ancient cosmologies placed Earth at the center of everything, with celestial spheres rotating around us. This geocentric view felt natural because it matched direct experience. We do not feel the Earth moving, and celestial objects appear to circle us. The geocentric model was not just emotionally satisfying, it was supported by the best observations available at the time. The Copernican revolution overturned this view, demonstrating that Earth orbits the Sun rather than vice versa. This demotion from the cosmic center was philosophically traumatic. If Earth is not central, what makes our position special? The answer became clear over subsequent centuries. Nothing makes our position special. Earth is one planet among many. orbiting an ordinary star in an ordinary galaxy among billions of galaxies. This progression of demotions became a guiding principle in cosmology. The Copernican principle, as it came to be known, states that we do not occupy a privileged position in the universe. This principle evolved into the cosmological principle, the assumption that the universe is homogeneous and isotropic on sufficiently large scales. No location is fundamentally different from any other location when you average over large enough regions. This principle is not just convenient mathematically, it is philosophically satisfying because it removes any hint of anthropocentrism from cosmology. The KBC void challenges this comfortable narrative. If we live inside one of the largest and deepest voids in the observable universe, our location is unusual by definition. We have not returned to geocentrism, there is no sense in which Earth is at the centre of anything. But we may occupy an unusual location nonetheless, one that affects every measurement we make. This is philosophically uncomfortable because it reintroduces a form of observer bias into cosmology. Observer bias refers to systematic errors introduced by the observer's position or perspective. In a homogeneous universe, observer bias should be negligible because all locations are equivalent. But in an inhomogeneous universe with significant structure, location matters. Observing from inside a void produces different results than observing from inside a filament or cluster. The observations are equally valid, but they represent local conditions rather than cosmic averages. This raises the question of what we mean by understanding the universe. If our observations are biased by our location, are we learning about the universe as a whole, or only about our local environment? The answer is both. We are learning about our environment, and by understanding how that environment affects our observations, we can infer properties of the larger universe we cannot observe directly. But this inference requires assumptions about how structure forms and evolves, assumptions that themselves depend on observations that might be biased. Some philosophers of science argue that all observation is theory-laden, meaning we cannot separate what we observe from the theoretical framework we use to interpret observations. The void exemplifies this idea. We cannot observe the void directly. We infer its existence from comparing galaxy counts to theoretical predictions. If those predictions are wrong, our inference about the void could be wrong. But we test predictions using observations, which brings us full circle. Breaking this circularity requires multiple independent lines of evidence that converge on the same conclusion. The KBC void is supported by galaxy counts, velocity measurements, baryon acoustic oscillations, and consistency with the observed Hubble tension. Each line of evidence has its own assumptions and potential biases, but the convergence of multiple independent techniques strengthens confidence in the void's reality. This is the standard scientific method for dealing with theory-laden observation. Another philosophical issue concerns the anthropic principle. This principle states that observations of the universe are necessarily biased by the requirement that conditions allow observers to exist. We could not observe the universe from a location or time where observers cannot exist. So the fact that we find ourselves in a place where life is possible tells us something about cosmic structure. Applied to the void, the anthropic principle might suggest that observers preferentially arise in voids rather than in dense regions. Perhaps the reduced frequency of catastrophic events in voids, such as nearby supernovae or gamma-ray bursts, provides more stable conditions for life to evolve. If most observers in the universe live in voids, then finding ourselves in a void is not surprising even if voids are rare by volume. However, this argument only works if voids are indeed more conducive to life than other environments. It is not clear that they are. Void galaxies tend to be less massive and chemically evolved than galaxies in filaments, which might make them less suitable for complex life. The argument requires empirical support, which we lack because we have only one example of life-bearing conditions, our own. The selection effect is real regardless. We can only observe the universe from locations where observers exist. But whether this meaningfully explains why we find ourselves in a void depends on details of how life arises and in what environments it is most likely. Until we have a better understanding of biology's relationship to cosmic structure, anthropic arguments remain speculative. A different philosophical angle concerns the problem of induction. How do we generalize from a single observation point, our location in the universe, to conclusions about the universe as a whole? Classical philosophy recognized that induction, reasoning from specific cases to general principles always contains uncertainty. We observe the sun rising every day and induce that it will rise tomorrow, but this inference is not logically certain. In cosmology, we observe the universe from one location and induce that other locations would show similar properties if we could observe from them. The cosmological principle codifies this induction, assuming uniformity. But if we live in an unusual location, our inductive inferences could be systematically wrong. We might conclude the universe expands faster than it actually does because we are measuring from inside a void. Without the ability to observe from multiple locations, we cannot test our inductive inferences directly. This limitation is fundamental. We cannot move to another galaxy to check whether measurements from there agree with measurements from here. We are confined to our single vantage point and must work with the data available. This makes cosmology challenging in ways that other sciences are not. A chemist can run the same experiment in different laboratories to check reproducibility. An astronomer cannot observe from different locations in the universe to check cosmic homogeneity. The best we can do is observe distant regions and assume that what we see there represents conditions throughout the universe. But even this has limitations because we observe distant regions as they were in the past, not as they are now. And our observations necessarily pass through our local environment before reaching us, potentially picking up biases along the way. The integrated Sachs-Wolf effect is one example of how local structure affects observations of distant regions. Despite these philosophical challenges, progress is possible. Science has always dealt with observer bias and theory-laden observation. The key is transparency about assumptions, careful analysis of systematic errors, and seeking multiple independent lines of evidence that converge on the same conclusion. The void hypothesis is being tested through multiple techniques, and future observations will either confirm or refute it. This is the scientific method working as intended. What the void teaches us is humility about claims to cosmic knowledge. We should hold our conclusions tentatively, always open to the possibility that new observations will overturn current understanding. The history of cosmology is full of surprises, from the discovery of cosmic expansion to the acceleration driven by dark energy. The void is the latest surprise, and it reminds us that the universe is under no obligation to conform to our expectations. Looking forward, the question of cosmic location and observer bias will become increasingly important as observations reach greater precision. Every percentage point improvement in measurement accuracy makes systematic errors from our location more significant relative to statistical uncertainties. Understanding and correcting for these biases is not optional. It is essential for progress in cosmology. The void also illustrates how scientific progress often comes from recognizing problems rather than solving them. Identifying that we might live in an unusual location does not immediately solve the Hubble tension or other cosmological puzzles, but it reframes the questions and points toward productive research directions. Sometimes recognizing the right problem is more important than proposing solutions. For now, we stand at the edge of understanding, peering into the void that surrounds us and wondering what it means. The universe has revealed itself to be stranger than we imagined, and our location within it more peculiar than we ever suspected. We're inside a cosmic hole, measuring the universe from the outskirts, and only time will tell what truths we uncover from this unlikely vantage point. If this journey through cosmic emptiness has changed how you see the universe, hit that like button and subscribe for more explorations of the cosmos. The universe is full of mysteries, and the void is just one of them. There is always more to discover, always more to question, and always more to explore in the great cosmic desert we call home.